Why is conformational analysis so important? Well, Sir Derek Barton demonstrated that the conformational orientation of a substituent relates to that substituent's reactivity, and for this he got the Nobel Prize in 1969. In our simple cyclohexane locked with a tButyl group, we shall consider how nucleophiles or electrophiles will interact with our reactive groups X or Y. In this case, hydrogens are of particular importance. Let's think of our nucleophile or electrophile approaching from the top face. Well, the nucleophile or electrophile is going to have a significant steric interaction with two axial hydrogens on the third carbons from the XY carbon. This makes such a facial attack unfavorable. What about the bottom direction? Well, now there's no such unfavored interactions, so this facial attack is more desirable. Let's look at some examples of conformational influence. In the first case, an alcohol reacts to become an acetate using acetic anhydride and pyridine. We have a choice of substrates between axial or equatorial alcohols, but how does that impact upon reactivity? Here, the equatorial alcohol is 3.7 times faster than the axial alcohol, because to react with the axial alcohol, the reagents must approach from the top face that's sterically hindered by the axial hydrogens attached to the third carbons from the alcoholic carbon. In our next reaction, we're looking at the esterification of a carboxylic acid with acidified ethanol. Here, the equatorial carboxylic acid is 20 times more reactive than the axial carboxylic acid. For this axial carboxylic acid, the reagents must approach from the top face, and that's sterically hindered by the axial hydrogens attached to the third carbons from the ring carbon attached to the carboxylic acid carbon. But more importantly, when viewing the intermediate, we realize that it has a similar shape to a tButyl group, and we know that an axial tButyl group, and by extrapolation, the tetrahedral esterification intermediate, has strongly disfavored 1,3 diaxial interactions. Lastly, what about the tosylate's reaction with a thiolate? Now, the axial tosylate is 30 times faster than the equatorial tosylate, so the opposite result to the last two examples. What's going on? Well, the result is different, but the rationalization for the result is the same. To react with the equatorial tosylate in an SN2 fashion, the thiolate must approach the tosylate's ring carbon from the opposite direction to the ring carbon tosylate bond. That's to say, from the top face. That again has the same unfavorable steric interactions with the axial hydrogen's 3 carbons from the tosylate's ring carbon that were encountered in the last two examples in the axial situation.